Chemical Engineering at the University of California, Berkeley. And she did her PhD, her bachelor's from MIT. After that, she moved on to postdoc with Jason Fleischer at Princeton University, and she was a lecturer there. And then she recently moved to UC Berkeley. So welcome here.
Thanks. Thanks for inviting me. Do you have the clicker, or do I have to? If I stand here, is it better? No, this should be fine. Laser pointer. Oh no, I just didn't want to be walking in front to change slides. It's fine. Maybe turn off these lights. Okay. Thanks. Front. Nope. It's okay if it doesn't work. Okay, thanks. All right, thanks for inviting me. So this talk is about computational imaging, specifically with different systems that use partially coherent light. So a couple different ways of looking at this situation. So this is kind of an outline of stuff that I'm going to talk about. And I did do my postdoc with Jason Fleischer, who does nonlinear optics. So I'm not going to talk about that because I assume that he already did in this seminar series. But basically, I'm going to talk about different forms of full wave field imaging. So measuring enough properties of a wave field that you can manipulate it, like digitally propagate it or something, something equivalent. And then some stuff at the end on new stuff that we're doing with coherent synthesis, as well as measurement. OK, so when I talk about partial coherence, I mean spatial partial coherence. So I'm talking about quasi-monochromatic and temporally stationary beams, because anything away from that is more complicated. That's the only reason why. So the other thing I'm ignoring is polarization. I assume that everything's the same polarization always. And so any temporal coherence effects aren't going to necessarily come into play, although they're related. So if you stay within that regime, you can argue that you could split your different imaging methods up into these three. Coherent imaging methods are basically looking for phase. So if you have a coherent beam, you can measure its amplitude and phase. You have a full measure of that wave field. If you have a totally incoherent beam, neither of these actually exist, but in this limit, if you have totally incoherent sources, then you can treat everything with ray optics. Who cares about the wavelength or the phase effects? And you can talk about this in terms of light field imaging is just one, but generally the ray optics limit. And then in the middle, you have this partially coherent regime, spatial partial coherence, where it's a little bit of both, and things become more complicated. So generally, this regime is kind of avoided because it's more complicated. But it also provides a lot of opportunity for doing more things because it has higher dimensions, which is what makes it more complicated. So within both phase imaging and coherence imaging, you can split up the measurement techniques into interferometric and non-interferometric. These are kind of arguable, but in general, interferometric, you need a really nice temporally coherent laser. Coherence imaging you can also do by interference effects, but there's also non-interferometric versions that tend to be experimentally simpler that I want to talk a lot about today. So here's a super simplistic view of spatial coherence. If I have a coherent beam, then any point along the beam is only traveling in one dimension. It only has one amplitude and one phase associated with that point on the beam, and the slope of the phase determines what direction the energy is propagating in at that point on the beam. So you can fully describe these beams by amplitude and phase. A 2D complex function is enough to know what's going to happen at a later plane as this thing propagates. With a partially coherent beam, at every point in space, x, y, I have a two-dimensional distribution of directions that the light is propagating, or equivalently a two-dimensional distribution of phases or spatial frequencies that exist at that point. This is why we often call it statistical optics, because we're talking about probability distribution. But if we average over a lot of instances, then we can have a known distribution, but it's always going to be a four-dimensional function because of this, because you can have a different distribution at every point in space. OK, so if you have coherent light, then what you want is the phase. You can measure amplitude with a camera. All cameras measure intensity. but you can't measure phase directly. So phase imaging has to be a computational imaging problem because you can't possibly measure it directly because it's changing way too quickly at optical frequencies to be measured directly. So you have to find a trick to convert phase information into intensity information so that you can recover the phase computationally afterwards. There's a lot of methods for this, and these are only a very small subset. But in general, you can have some that are interferometric versus non-interferometric, especially the Shek-Hartman, used a lot in astronomy because the light is incoherent, or the sources are incoherent. And some iterative methods that are kind of a mix of both. But what I would focus on for my PhD work was on this transport of intensity method. So I'm going to talk a lot more about that only because that's what I worked on. So the idea of this transport of intensity method is that you have some flat wavefront, say, impinging on a phase object. So it delays the phase by a certain amount that's relative to its surface shape and refractive index, right? So if I put in a flat beam, these are the wavefronts, these blue lines, and the gray lines are the associated rays, or the local direction of energy propagation, the eikenals really. And they are always, they're defined as being perpendicular to the wavefront at every point in space. So if you use interferometry, you're generally trying to measure this wavefront shape. But the transport of intensity takes a different tact and tries to look at the sort of the deviation of these local rays. And the way you can do that is just by measuring at different planes, measuring intensity at different planes along the optical axis, so the direction the light is propagating. And if you can measure the derivative of intensity along the optical axis, you can solve this equation for phase. So I is measured, you measure intensity in the focal plane. You should know lambda, and then you're going to measure this so you can solve for phase, right? So this is the basis of this technique, and there are issues. This should be recognized that if intensity is constant everywhere, this becomes the Laplacian of the phase is proportional to this derivative of intensity. This is just a local continuity equation. So generally, you need boundary conditions. We tend to just avoid them because of the number of degrees of freedom that we have here that they're not as important. But the idea is that you have a very simple experimental setup. Instead of building a Mach-Zehnder interferometer or something like that, which is very sensitive to vibrations, I can just take two pictures that are slightly defocused from each other. And you might have an imaging system in here so that you're measuring one focused image and one out of focus. So some of the other nice advantages are that I pointed out that this could turn into a Laplacian if I is constant. And so then it becomes a Poisson equation. And we know very well how to solve Poisson equations numerically. And we can do it in the FFT domain. So it becomes a very fast, simple reconstruction method. But one of the very best parts of using the transport intensity is that it can be used for partially coherent light. And it started out with X-rays where they just weren't that coherent. And so this is a plot of just the spatial frequencies that you can get in a microscope with a given aperture ratio of your condenser to your objective. And it shows that your transfer function is the same. You get the same spatial frequencies that you get through the microscope normally in your phase result, basically. OK, so here's an example. These are two defocused images. I just turned the knob on the microscope slightly and took the two pictures. They look very similar. But if you take the difference between them, compute this derivative, and solve the transport of intensity, you can get a map of the cell's phase, which is shape and refractive index mixed together. Mm-hmm.
If it's partially graded, what is this phase of?
Yeah, so this is the average phase that a coherent beam would have seen for a coherent beam of wavelength lambda, which is the mean wavelength. So doing this equation, summing over lots of different wavelengths is fine. You can just take the average, the weighted average of the wavelengths.
So if your phase is constant, there is no change in intensity, even with partially coherent beam.
So you're measuring a phase change, right?
Well, I just look at this equation. You say it's also partially coherent beam. So if phase is constant, the average phase.
Yes.
The IO is here.
So what is constant?
It's not what we see in experience.
So what is constant is the change in phase from this side of the object to this side of the object. That is a constant phase change for a given wavelength. So some people call it the real part of the refractive index, but really it's, I assume that I've put a plane wave. I don't know what the exact phase is at the input, but I can measure the change in phase from the input phase relative to all the other points in the xy plane. And then as you get more spatially incoherent, it breaks down and it's not really true anymore. Because as you defocus for very spatially incoherent light, you don't get any information about the in focus plane. So you start to blur things out as you decrease the spatial coherence. And as long as that blur function is smaller than your PSF, it doesn't matter. Okay, so, and this is a plot basically, decreasing coherence. So this is in a microscope, changing the incoherence parameter. So just opening up the aperture and closing the two apertures, probably just moving one of them relative to the other. And what you see here, so this is for a very specific experiment, but what you see here is that so you want it to be coherent. The whole thing is derived for coherent light, spatially coherent light. But as you decrease the coherence, nothing happens until some specific point where it starts to degrade. And that point is going to be when the blur due to coherence becomes equivalent to the blur that you already had in your system, or like your pixel size or your PSF, whatever is your limit. It totally depends on geometry. And since you're propagating very short distances, the distance actually matters. The further you go, the more blurring you get. So if you go shorter distances, then you can go further into incoherence. So when I say that it works for partially coherent light, I don't mean it arbitrarily works for partially coherent light. In fact, this paper showed that if your source is 2 point sources, so you have 2 plane waves illuminating the object in different directions, then when you defocus, you get 2 copies of the defocused image. And if you try to recover phase from that, it will be wrong, unless you take into account knowledge of what your source was. So this is all assuming, and this was all worked out in the original papers for the transport of intensity, that the conditions are that your source needs to be rotationally symmetric, so basically a circle on axis of a size that's small enough relative to the distance of defocus, which is totally geometry dependent. But the point is that you can use a white light microscope and you can get good results, which you cannot do for interferometry. So it's less sensitive to decreased coherence. It's not totally insensitive. Okay, so here's an example point. And these are all generalizations. This is just for some test object. So I'm comparing now transport of intensity with the standard iterative method. So just back and forth propagation replacing with intensities that you've measured. And as you increase the distance between your measurements, which method is better changes. And this is completely object dependent. So this is only for one case. I don't promise this is true for any other case. But also what you see is as I decrease coherence, the transport of intensity degrades much less quickly than this iterative method because it's not relying on diffraction, which is what gets blurred out when you have partial coherence. So these are gross generalizations. You can break these trends if you really want to. Okay, so the project that I was most interested in when I was doing this was that we said that instead of propagating 2 different distances, there's a wavelength distance degeneracy. So I can equivalently propagate 2 different wavelengths, 1 distance, and it's the same thing. I still get 2 defocused pictures, right? So it turns out that just free space propagation is really crappy. You just don't have enough dispersion between those 2 colors for a small defocus distance, which you want because you need to get back the focused image. You want a focused image result. But if you put it into an imaging system that already has dispersion, this dispersion is enough to get well-separated defocused images of approximately the right amount of defocus to get back what you want. So you can write an equation. It's just the exact same equation, but swapping lambda and z. But the practical advantage is that now I can focus this system at green, so put my camera in the green plane, and green will be in focus, and the other 2 colors will be oppositely defocused, which is exactly what I wanted to measure, but now I'm getting it in 1 measurement. So everything's perfectly registered. There's no motion artifacts, and I only take 1 picture, and I sacrifice spatial resolution by factor 4. So I really like this paper. These people showed that jumping spiders actually have a mechanism in their eyeballs to use the chromatic aberration of their eyeballs to know how far some target that they're trying to jump on is. So they killed the color artifacts, and these spiders weren't able to hit their mark ever. So it's a bio-confirmed design. But one thing that's nice is you can also choose the focal lengths of your lenses in order to choose how much defocus you get between the colors. So you can tune it to some degree. Of course, you're also trading off field of view and NA. So it has to fit within whatever you're trying to measure. So this is the first experiment. I did just take a white light source, collimate a white light source as best you can, bounce it off a deformable mirror, thin sheet of aluminum with actuators behind it, and then build a 4F imaging system that intentionally has well, I didn't have to do anything. It has chromatic aberrations in it. But the phase then is a function of the surface height on the mirror. So what we want is a 2D map of the surface height of this mirror from a single color image at the camera. So here's what we get at the camera. These are the actuators, the little black dots there. And you can see something's happening in this X-forms. There's some blue color changes. And so we want to take this picture and quantitatively recover phase. So split it into its color channels. The green color channel is perfectly in focus. A perfectly in focus imaging system has no phase contrast. And the out of focus in either direction imaging systems have opposite phase contrast. So phase goes anti-symmetric about focus. Amplitude effects go symmetrically about the focus. That's how you separate the two from these three images. So we take these three sub-images taken from the same color image, and we can get back this surface profile. So here you can see the actuators. This is actually inverted. They're actually pulling down instead of pushing up. But you can see the little tents they create between them. It's a couple microns high. And then this is dynamically changeable, so I was just having fun. But it compares very well to commercial white light interferometers. This was a Zygo that we compared to. So this is an influence function. That's you take your deformable mirror and just actuate one actuator and plot its influence function. But you can see here something happening in the interferometer result. And what it is that this is a very steep phase slope. It's multiples of 2 pi, right? So the phase unwrapping algorithm here screwed up something. It seems to be a very naive phase unwrapping algorithm, but it creates this streak artifact because that slope was too high for the unwrapping program. And transport of intensity, you're measuring the second derivative of your phase, so that tends to have much lower slopes, so you don't alias as quickly.
So what's the light source?
It's just a white light, like I think a halogen lamp. Mm-hmm.
Do you need to control somehow the coherence of blue, red, and green, so it's the same?
So in this case, I had a white light source, and it wasn't a pinhole, it was an iris, and I just closed it up. So it's like 1 millimeter big with, say, a 15 centimeter focal length. So it's pretty coherent, spatially coherent. The temporal coherence doesn't matter. Within the visible range, temporal coherence won't make a big difference ever. But spatial coherence does matter. If I had opened up that iris, it would start to degrade my result in the way that I showed in that plot. So I'm intentionally making this fairly coherent, which you can do in a microscope. And I'm going to show some microscope pictures in a minute. So the next step that we wanted to do was, the whole advantage of this is that it's single shot. It's really easy to do. And so you can take a video and then process it to do really fast things. The frame rate of your camera is your limit, right? Our cameras had a pretty crappy frame rate. But what we really wanted to do was to make a microscope where you can see quantitative phase in real time. So my lab mate was a GPU expert. So he just threw everything onto the GPU. It took him about a day after I spent a week trying to do it. And he can do things in milliseconds. So we were completely limited by our camera bringing in the data. So our GPU was computing faster than the camera could bring in the data. And we didn't have a faster camera, but we projected that the GPU would keep up with the camera up until you got a camera of 2,000 frames per second. Then you would be GPU limited, and you'd have to buy a more expensive GPU. And this was so this is space bandwidth product, so you can also include how many pixels you're doing.
Did you compensate for the Bayer filter pattern?
So we intended to, but it didn't make a difference, so we just didn't bother. So in the GPU implementation, it's not in there because it didn't matter. So basically what you can do is, and this just happened to be true, is that you can set the PSF of your imaging system to be at least as big as the 4 pixels set in which case it's not an issue. And that just happens to be true. In fact, in most microscopes with color cameras, if you just buy them like that, that will usually be true. I don't know if they design it.
Sorry, your camera is essentially a black and white broadband camera with RGB filters on top of it.
Yeah.
Right? So does the specific spectral transmission characteristics of the filter factor into your calculations there?
It does a little bit, in that choosing what we use as RGB has to be the spectrally weighted mean of the red channel, the spectrally weighted mean of the green and the blue. And so actually, because of the Bayer filter pattern, I had intended to use a Foveon camera because each pixel measures all 3 colors, which is good, right? That should solve all of those problems. The problem is that if you look at the spectrum, I wish I had backup slides, but if you look at the spectrum of a Foveon camera, kind of like red, green, blue, and they say that's good because you can really pick up these colors that are in between the 2 channels very nicely. So they say you get better representation of those colors in the middle, but that's really bad because we want our colors to be separated. So I say it doesn't matter, but if there's a lot of crosstalk between the 2, it could matter. But the Bayer filter cameras tend to have filters that are pretty sharp, and then it's not as big of an issue. Okay? So here's some real-time images. They look surprisingly similar. So now I'm into a microscope, right? And an obvious question with a microscope should be that microscopes usually have much better lenses than the ones I pulled out of a drawer in our lab. So in a regular microscope, you will have chromatic aberration correction. So how can you possibly use chromatic aberration to your advantage? And so this is actually a nice trick. If you use just an achromat, so not any super fancy aberration correction, but just an achromat, basically what you've done is you've corrected the focus shift to be exactly the same for 2 specific wavelengths. You can never correct for all of them at once. And so instead of having this linear or almost linear focal shift with wavelength, you have kind of this bowl function. So if you know how the achromat is designed, then you can use that to just compute your intensity derivative in a different way. So for this one, which is what we happen to have in the lab, we basically say that we're going to use, so this is the red, this is the blue, and this is the green. So we're going to average the red and blue because they're at the same focal shift. So that's good because before we were only using 2 colors. Now we can use all 3 because we're averaging these 2 and then using green as the other one. So the average of red plus blue, the average of red and blue, and then the green one are the things that you subtract. And that's really nice because Bayer filter has twice as many green pixels as it does red and blue. So when you add the red and blue, then you're coming up to the same sort of noise levels as you get for the green already. So you're just kind of taking advantage of what already exists. So if you just use red and blue, they have pretty much the same focal shift, so you get a crappy result. Whereas if you do this achromat version, you get a nice result. And so we did a lot of imaging in various microscopes because there's no hardware changes here. You just put a color camera. And in some cases, here you can see it's a bit noisy. So this was with a fancy achromat. So we remove that and put in an intentionally uncorrected one, and you get better images. OK, so something about TIE, it's not perfect. Its limitations are very different than the limitations of interferometry. So it is a well-posed equation. So theoretically, you can get perfect phase recovery from it. But it's very unstable with noise. And this is the problem. This is the whole problem. The equation itself is fine. The problem comes in this derivative measurement. You have to measure the derivative by finite difference, or I don't know any other way. So you have to take one, subtract the other, divide by the difference. So if intensity was linear with z, then this would be no problem. You could take a large z and get good signal-to-noise ratio. Everything would be great. But it is not linear with z because intensity is not a linear function with phase. Intensity is bilinear with phase and amplitude. And so you're forced to do small dz in order to keep things in this linear approximation. So this is the small defocus limit is the same as this linear derivative approximation. And what happens is that your noise gets divided by a small z number. And so this is very unstable, right? So this is the linearization that happens because it's not a linear problem in general. And the linearization is true if you could measure that linear derivative perfectly. So here's an example, another test image as I increase dz. So small dz is good for keeping this linear derivative approximation accurate, but in large dz you get error due to that nonlinearity. But small dz means you're noise sensitive, and so things blow up if you go too small. So here's the best image that you can possibly get from this specific object. And this curve is completely object dependent as well as noise dependent. So here's a picture. If you have too small of a dz, you get a lot of noise. Noise hits the high frequencies more than noise hits the very high frequencies and the very low frequencies the most. So you get this kind of cloudy effect. And if you go too far, then you get these nonlinearity effects, which look like diffraction, right? Because diffraction is exactly what's not being accounted for. So these are all object dependent. So I have a very hard time to generalize how you should do this because it depends on the geometry. So one solution we were after was to say, well, if I'm going to say I'm doing this in a microscope and I'm defocusing the microscope, then if I'm going to move that stage and take another picture, I might as well take a video as I go through a lot of different focus positions. And that should be better, right? So our transfer function has some zeros. They should move around. We were looking for an algorithm for this. And this was the first one that we came up with, was to say, we did a very long derivation of taking this linearization and including the second order version of it. And what it comes out to is a lot of math that tells you that it's just your derivative measurement that's the problem. That you're assuming a linear derivative, which is not true. And so all these higher order terms are exactly what causes the error. So if you can measure these higher order terms, you can just subtract them from your linear measurement and get a better approximation to the linear measurement. So what that amounts to in the end is you're just fitting each pixel's intensity versus z to polynomials of progressively higher orders depending how many pictures you have. So this works. So this is a phase object. And as you add more images, so first order has 2 images, 20th order has 21 images. And you see the error drops off significantly as you add more pictures. This is kind of expected. I have 21 pictures versus 2. Of course, I should do better. But what's interesting is that the error is happening only at the sharp edges of the phase object, right? But that's exactly where diffraction happens. So this is the nonlinearity error, which is caused by diffraction. And so this is what you're correcting for as you add higher orders. OK, so we did the experiment, and it works pretty well. You get better images as you add higher orders. The problem is that in an experiment, you have noise. When you're fitting to higher order polynomials, how many orders should you fit to? If I take 100 images and fit to a 99th order polynomial, well, it's not necessarily better than 20 if what I'm doing is fitting to noise. If those higher orders don't exist and I'm just fitting them anyways, they're actually going to make the result worse. And the crossover point where it becomes worse instead of better is completely object dependent and noise dependent once again. So it's impossible to know exactly when to stop. So this really bothered me, and it led to this project. It was a collaboration with my roommate, and she does Kalman filtering. So we said the Kalman filter is sort of the optimal inclusion of your noise information, the optimal smoothing of a set of dynamically changing data. So we did this. It's a fairly straightforward application. I'm not going to explain how it works. But basically, for a signal-to-noise ratio of 1, so your noise is just as strong as your signal, all of these other techniques have major problems because they don't consider noise. But the Kalman filter does a very nice job of smoothing out that noise. And you can get very close to the theoretical optimal of what you can achieve for this estimation. The problem was that this picture took 24 hours to compute because it involves a Kalman filter, which keeps track of covariance matrices, which for an n-squared image is n to the 4th in size. And you have to invert a matrix of that size, which is not possible. You have to do some fancy tricks to do it. And so we even had to block this up into 4 chunks. The nice thing is that I started a collaboration with some people who know this signal processing stuff very well. And they come up with a sort of an augmented version of this where they can prove that certain elements of the covariance matrix will be 0. And so you will have a sparse covariance matrix, in which case you can get a just as good result. In fact, it's slightly better because it doesn't have these crosses in under a second. So now this is actually something that could be real time, which I'm really happy about. Okay, so kind of moving in the other direction, we already had a question on this, which is great. But the idea is that interferometry doesn't measure absolute phase either, right? You measure the phase difference from one arm of the interferometer to the other. Nobody can measure absolute phase exactly that I know of. You're measuring phase changes from something else. And this is the same as what we're doing. So we're using partially coherent light, but we're not measuring anything about the partial coherence. We're assuming that the partial coherence is of a nice form so that we can get the phase change of the object, nothing about the illumination. If we want to measure the coherence properties of any arbitrary beam, then we have to do a much more difficult measurement. It's going to be 4-dimensional. If you can do it, it's great. You can do all of these things like digital holography, digital refocusing, aberration correction, all the things that you can do with coherent light. When you know the full wave field, you can manipulate it and you can predict how it will pass through linear systems and some nonlinear systems. But this is really sort of fundamental interest because almost all light is partially coherent. And so with my definition, only lasers are fully coherent. And these partially coherent beams are 4-dimensional, so how can we measure them efficiently? So my picture of partial coherence is this beam with different propagation vectors at every point in space. And you can relate these to all the different ways to represent partial coherence. Most people pick one and stick with it, but in the end, and I don't have the reference, but there's a paper that they're all mathematically equivalent. You can write unitary mathematical transforms to go between any of these different representations of second-order coherence properties. So I'm going to talk about these two today because those are the ones I'm using. So say you start from the cross-spectral density correlation in space and time, and we want it to be easier. So even though space and time are related, let's only talk about space. So let's look at the mutual intensity just to make everything easier. So now this is only a correlation of a complex wave field at different points in space, right? And these brackets indicate an ensemble average over some statistical ensemble. In our case, it's going to be a time average. So the traditional way to measure it comes directly from the math. Okay, I want to correlate 2 points in space. Let's pick out 2 points in space, interfere them with each other, and see how well they correlate. If they correlate, you get interference fringes. So this is sort of the traditional way to measure it, but you have to then do a 4-dimensional scanning of these 2 pinholes. And say you measure a 2-dimensional picture, you're only going to extract one scalar parameter from it, the fringe visibility. So that's very wasteful. It's a lot of scanning. So this group at Duke just put this into a rotational shearing interferometer so that they could reduce the scanning by a dimension. And so they were using it for 3-dimensional. So they assume this object is incoherently emitting in 3 dimensions. And then if they can measure the coherence functions coming from the object, they can figure out all the 3-dimensional incoherent intensity points where that object emitted. And so they get a really nice result from this. But one thing to note here is that they have a pretty small number of pixels. It was a fairly long time ago, but the limit on this is that you have to do an inversion algorithm. And when you get up to, as soon as you add more dimensions, you get problems with these inversion algorithms, whether they're even possible in those high dimensions for high resolution. Okay, so now I want to transform this into another representation because that's the one that I'm using. So I take my mutual intensity function. So here's an example of an object with 3 bars that has this correlation function. So it's 3 bars that are all correlated with each other, coherently illuminated. If I just do a change of variables in a Fourier transform, I can get to the Wigner distribution function. So this is the unitary transform from mutual intensity to a Wigner function. How many people have heard of Wigner function? Okay, so the idea of Wigner function is just that you're describing both space and spatial frequency at the same time. And it ends up being, this is the mutual intensity function with a shifted coordinate system. And you do a 1-dimensional Fourier transform of that shifted coordinate system mutual intensity function. And the coordinate system is a sum and difference because you want to be going in equal directions on either side to correlate those 2 things. And so when you plot the same beam in Wigner function space, you see x versus spatial frequency. So you see here that at the edges of that object, you get lots of high frequencies because there's lots of diffraction to higher orders there.
Is your mutual intensity semi-close to this one here?
Yes. Yeah, so I'm only showing the real part of this. So the Wigner function is always real. The mutual intensities, I'm only showing the real part here. So this is basically the mutual intensity if I took 3 holes and I illuminate them with coherent light. So each one of the 3,
So where's the randomness in averaging?
Sorry?
Where's the randomness in averaging?
So there is no randomness if it's coherent.
Yeah, so
In here, you can have some randomness.
coherent light, right?
This is, yes. Yeah, and this is a coherent Wigner function. Yes. Okay, so this is what everybody shows when they talk about phase space. So Wigner function is one version of phase space. And it's a way to plot frequency versus, in this case, time. In our case, it's space. And spatial frequency. This is time and temporal frequency. And so if I give you a musical score, I can't just tell you which notes to play. That doesn't make a song. I can't tell you when to play a note. I have to tell you which notes to play when. You need both. So this is the same idea for these 4-dimensional beams. So this would be 2 of the 4 dimensions. So the idea is that you need all of these. So it is, you have this higher dimensional. So I took, in the coherent case, I'm taking a 2-dimensional beam and converting it into a 4-dimensional representation. That's completely wasteful. But in the partially coherent case, it is 4-dimensional. So I have to, so it's not as wasteful to represent it in this way. Okay, so typical example. This is space. This is spatial frequency. And in the paraxial limit, spatial frequency is directly proportional to the angle of propagation. So before I was drawing angles of propagation, this is the general relation. So you can think of this as the angle variable, which is what is used in light fields for ray optics. So, and this is just a schematic. So if I have a point source, it exists at one point in space, but it's giving off light with all spatial frequencies, or in all possible directions. Plane wave is the exact opposite. It exists at all points in space. It's only traveling in one direction with one spatial frequency. And a spherical wave has a linearly increasing chirp as you move away from the center of the sphere, right? And so it's moving, if you think of this as direction, this is to the left, this is to the right. And so, so you take a quadratic phase function and you convert it into a purely real sort of linear mapping in phase space. So this is where all of the nice numerical properties come from. So one way you can think of propagation is as a spherical chirp convolved with whatever your object is, so that your final result after propagation is just a sheared version of your original object. So this is basically you're taking what would normally be for partially coherent light a lot of different quadratic phase integrals over every coherent mode, say, and turning it into just a geometric shear in phase space because it's just the way you're storing the information. So basically this is all just matrix optics. So you can win a lot in terms of computation because the computation becomes much simpler in this case. Okay? Okay, so looking at phase space, if I project at all, if I look at one point in space and I sum up all of the different spatial frequency informations, or in the ray optics case, you're summing all the rays from every different angle that hits one point, then what you get is the intensity versus space. Similarly, if I sum up all of the different positions that are going in a specific direction or spatial frequency, I get my spectral intensity. So these are projections of this higher dimensional function. So this is where you can see that you can get more information. You can have higher dimensional things happening that appear the same in these projections. So another thing, and this is a total generalization, that if I look at the local spread of spatial frequencies, that is to some degree a measure of the local coherence width. So at this part of the beam, light is scattering to a smaller range of angles, and so it's more coherent than the light at this part of the beam, which is scattering to a higher range of angles or spatial frequencies. So the bandwidth across X is a measure of the local spatial coherence across X. If you buy that, great. So this is a really nice way to think of coherent versus partially coherent. My coherent beam, in this case, was a one-dimensional complex beam. So in phase space, it just fills out a manifold, a smaller dimensional manifold of the larger space. So a two-dimensional manifold of the four-dimensional space. Whereas in the partially coherent case, you can possibly fill in the entire phase space. So you have a lot more degrees of freedom for controlling what your beam's fundamental properties are. And if you look at the projections of spatial frequency that give you the intensity patterns, you also have a lot more degrees of freedom in creating intensity patterns with partially coherent light that can't be created with coherent light, although they're sort of limited on the edges in some cases. So people have been trying to measure these for a long time. This was one setup. So basically, they take a transparency, and they take 2 copies of it, and they want to correlate it with itself. So they put it through this roof prism, basically just flips everything, like left-right flips things. And then they can directly measure the Wigner function of a 1D purely real and coherent signal. So they get this nice dog bone shape again. So at the edges of the aperture, you have lots of high frequencies, and then you have diffraction effects. OK, so then this is a really elegant way to do it. Phase-space tomography says that intensity is the projection in this direction of the full phase space. So if I propagate this beam, it shears, similar to a rotation. In fact, you can write it as approximate to a rotation. Then you take the intensity projection of that slightly rotated version, and then you slightly rotate it, take the intensity projection. You're just doing tomography, right? So you're doing tomography of this phase space. And so this is phase-space tomography, that if you propagate to different planes and take these different projections, or just measure intensity at different planes, you can reconstruct phase space. So there's one problem with it. You're measuring 3-dimensional intensity, trying to get back a 4-dimensional function. So to actually do it properly, you need to add some astigmatism to your measurement. So this is sort of the end result of what you should do, is to have 2 cylindrical lenses, and you take different pictures of them moving in different planes and having different focal lengths. But you're still taking intensity measurements and to get rotations of phase space. And it turns out that this work, the astigmatic coherence sensor, was derived in a completely different framework for mutual intensity measurements. But it turns out to be very, very experimentally similar. In fact, they're measuring just different ways of measuring the same thing. And it's really nice to compare these two in how they do these things, basically the same thing. So my old lab mate, Lei, looked at this in terms of compressed sensing. So if you take a tomography, there are certain angles you won't get. You can't propagate to infinity. OK, you can put a lens and do a Fourier transform. But you're going to be missing some angles. So he was saying, can you use compressed sensing to recover those or guess what they are? And in the end, what he ended up using was this coherent mode theory, and saying that this thing is probably sparse in how many coherent modes it has. So it has light coming in at a sparse set of angles. And they can get some pretty decent results. So then the other completely different way of looking at it is to say that if I have a 2D beam and I take an optical Fourier transform, what I measure is the spectral intensity. So I'm measuring the 2-dimensional spectral intensity averaged over all points across the beam. If I block all of the beam except for one point, so a windowed Fourier transform, then I'm getting the spectral information only from this one point. And so then if I scan this thing across the beam, I'm basically filling in different columns of the phase space. So this is an old idea that you're measuring a spectrogram, so it's literally a moving windowed Fourier transform, and you're directly filling in phase space. So it ends up being a convolution of the object Wigner function with the aperture. So you can do this with a lenslet array. You can, this is the way I originally tried to do it. Take a lenslet array, so it is basically an aperture with a Fourier transform. So what I would measure here would be the spectral information from this local piece of the beam. So I'm doing a bunch of different local Fourier transforms. So if I just reinterpret this Shack-Hartman measurement as a phase space measurement, I can get, this is a Gaussian beam, So great, I can get phase-space measurements. The problem is that I have a severe trade-off between space and spatial frequency resolution. So this picture looks terrible. It's bad resolution in both dimensions because we only have a certain number of pixels, and we have to trade them off one for one. So the Lenslet array is nice because it's single shot, but you're definitely limited by this resolution trade-off, and you're further limited by the fact that if the coherence length is bigger than the lenslet aperture, then you're not correlating any piece with the stuff that goes through the next lenslet. And so this is a limitation of what you can measure. So if you use a large aperture lens and scan it, you solve all of these problems, but you pay the price in speed that you have to scan. So we did this because we didn't care about speed. We were looking at nonlinear optics, and we just use our SLM as the scanning aperture just to make it fast. So it blocks all the light except for one small hole, and then we take the Fourier transform, and we look at real space just to see what's going on. So here's a couple of pictures with coherent illumination and partially coherent illumination of the same object. So coherent, you get all these diffraction effects. Partially coherent is just Gaussian everywhere. It was a rotating diffuser with Gaussian statistics. And then if you take pictures as you're propagating these beams, they shear in one direction and shear in the other direction. And once again, it's nice that the same thing happens for coherent and partially coherent light. It's just a shear. So we did this as a two-dimensional object with four-dimensional measurements. Our object's now this P. So I'm capable of doing, I have 1,000 by 1,000 pixels on my SLM and 1,000 by 1,000 pixels on my Fourier space camera. So I can take data that's 1,000 to the fourth. And I did, and it was impossible to process. So then I just cut it down. But you can do it. And then you can just look at these phase space functions. So you have this full measurement, but what can you do with it? So what you can do with it is something like digital refocusing. So this is just basically like super high resolution in all dimensions of light field camera, like what the Lytro does. And there's no 4D matrix inversion here. We're measuring things directly, so we don't need to care that we have a massive data set, other than we need to pick out pieces of it as we go. So here's some basic reconstructions. Okay. And they're pretty close to what, so this is actually defocusing it, and this is digitally defocusing. Okay, so last topic that I want to talk about is if you can measure coherent synthesis, you can probably invert things and actually create coherence patterns in 4D. So coherent synthesis has been around forever. Microscopists use it all the time. They just change the apertures on their microscope, the condenser aperture versus the objective, and that adjusts the coherence parameter, which is one scalar parameter. So that is a measure of the spectral width, assuming that you have a circular spectrum of totally incoherent light. And so you can do things with this, even with this one scalar parameter. So moving to more fancy, lithography puts different sources that are not just a circle now of different widths, but actually dipoles, quadrupoles. Dipoles if you want to print lines, so it's good to have things coming in two directions. And so this is basically two-dimensional patterning within this four-dimensional space. It's in the Fourier plane, so everything you do here is going to affect every point here. So at the object or mask plane, the illumination's homogeneous everywhere. It just has different directions of propagation. So 2D patterning of 4D. And there's some other examples. The rotating diffuser is a 2D patterning of 4D. You're patterning the shape by the statistics of the diffuser. And again, in real space, you see just flat intensity. So what we did was you have to put this in real space, a diffuser SLM. So it's just an SLM whose job is to be a diffuser, but instead of rotating so that you have the same diffuser pattern at every point in space, it's just changing really quickly, much faster than the camera's time. And it's just displaying different diffuser patterns that are temporally statistically stationary, but spatially not stationary. So some patterns. Here's an example. This is a case where I have some large speckle, small, large, small speckle. And so the time average of all of those is just homogeneous flat intensity. And so if you take the projection in phase space along at x, it'll just be fairly flat. And if you take the projection of all the frequencies, you just get this is sum of Gaussians. But if you look along here, you can see what's happening locally as the coherence is changing locally. So we did this in 4 dimensions. This is the best I can do to plot those. These are all the local spectra at different points in space. And these are the 2-dimensional projections of those 4D functions. Another one, this is an elliptical Gaussian that's rotating across space. So if you take the projection, you don't know where each of those components comes from. And in real space, the whole thing is just homogeneous. So you can illuminate things with, we designed this to be homogeneous in real space, but having these weird coherence properties across the beam. So you can potentially think of things you could do with this to do like designer illumination type stuff. So the reason why we're doing all this stuff was for nonlinear dynamics. I don't know if Jason already talked about it, but there's a lot of other applications in microscopy, aberration correction, getting into lithography lately. They're already using tricks in designer illumination, so what can they do with the full 4D? And then there's a lot to do with the algorithms. My scanning aperture is probably the worst algorithm you could use, so I'm working on different better ways of efficiently capturing this data quicker. So speed is another issue. And that's all. So kind of the general idea that we're doing full field measurements and trying to sort of add an engineering touch to it to measure these things efficiently so that we can actually measure these higher dimensional things that people generally think are worthless to measure or impossible. So I'll thank all of my past collaborators and colleagues.
So you really took 1,000 by 1,000 images?
Yeah, if you want the data set,
You actually
you're welcome to process it.
So is that an example of something that's ripe for application of intelligent sensing? You did one application of that.
Yeah. So actually, I wanted to do this. So I had this data set, and that's part of why I took the data set. So now we're talking with all the computer science people in my department, and it was like, how can we process this efficiently? There's not that much processing to do, so it's really not that bad. But I wanted to do adaptive things, like put this on a DMD array so you can go fast, and then like guess. So these 4-dimensional functions, if you're measuring like a cell or something, it's going to be compressive. It's going to be sparse in some of those dimensions. But if you can't a priori say which ones, you'd have to take a couple measurements and guess where it's sparse. And then you can do adaptive stuff. But then the problem is that these measurements can happen very quickly, so it might not be worth it, because your computation is going to be a big deal between each step. So I've kind of given up on the idea, because I think the computation of deciding the next best measurement is going to be take longer than actually just measuring everything and figuring it out later. So definitely compressive processing will happen and is already starting to happen. If you have an area that's all black, then let's stop worrying about that area. So if it's all black in real space, then you know the spectrum is all black in all those spaces, right? So there you can fill all those in.
With something like a moving diffuser, is it sparse in, what dimension is it sparse in?
So if you have a rotating diffuser behind some object, if your object is not changing the spectrum locally, then it's sparse in the sense that every point in space, in real space that has non-zero intensity, has the same spatial spectrum. So that's a rotating diffuser at a certain distance away. So that case is actually kind of the case where you're patterning the spectrum, but it's the same at every point in space. So you have like spatially statistically invariant. And so then you get to drop 2 dimensions.
Shell model coherence?
Yeah, so Gauss shell model is also.
It's not necessarily Gauss, just shell model.
Sure, yeah, that's the same idea. And so the thing I didn't talk about was coherence holography. So they have the same shape, spectral shape, but they can vary the width of that spectral shape across all points in space. So that's an interesting other way to cut up the function. But generally, everything is trying to cut it up, and usually patterning 2D because we have 2D patterners.
So in the first part, you were talking about images of phase object, transparent object, basically. There was a technique, and still is, called Schlieren technique, I believe. How does it relate to those work?
So Schlieren.
As a standard technique, I did a lab in wind tunnel in 1966, I think. We used the Schlieren technique to visualize
Yeah.
the flow.
So Schlieren was used for big things, right? really big things
Yeah,
because,
it was a big thing.
yeah, because you
The
can,
lens was about that big.
you don't need a coherent beam. But Schlieren is not quantitative. So it gives you some visualization of phase changes, but you don't get the full vector, right? So you can't separate amplitude from phase
I
information.
cannot see why not, but. I
You
think
could
it-
you could modify it to do that. Like, so you put a knife edge in half the plane, you could put it in the other half, and you could potentially get back
No lasers.
the other half. Yeah, so I guess so there's a group that was doing something similar to that, but they didn't have it in the Fourier plane. So I'm not sure how it exactly compares. But I've never seen anyone doing quantitative Schlieren with it in the Fourier plane of large things. Mm-hmm.
In knowledge of boundary conditions, part at least about the form of derivation, you didn't mention anything about.
Yeah, so they exist and they are. So if you take a transportive intensity experiment with 10 by 10 pixels and you have an object sitting at the boundary, you're going to have big problems because of boundary conditions. If you take 1,000 by 1,000 pixels with an object sitting at the boundary, it's not a problem because, especially like if you think about these Fourier domain techniques, every point in space affects every point in Fourier space equally. And so if you have error along the border, if that's like 1% of your image, the worst damage it could do is about 1%. This is not totally true, but on the order.
So you don't use any boundary conditions?
So well, we do. We assume that the phase at the edges is not varying across the edge. So you assume that if the phase is 2 pi here, it's 2 pi around the whole edge, which is not necessarily true. So you can do tricks too. So that's basically you're assuming periodic boundary conditions to solve the Poisson equation. So you can also like mirror flip these things, and then you have much more pixels, but you solve the boundary condition to some degree. So you can solve it with boundary conditions taken into account, but it's almost never a problem unless you have something that's covering most of the edges, like 3/4 of the edge pixels, and varying in phase across those pixels. So generally we ignore it because it's not really a problem, but it could be. Mm-hmm.
Will this work well if the detector is in the far field where you have higher implicitly frequent form?
So theoretically, yes, but practically it doesn't work very well because if you're looking at a phase object, the Fourier transform has a huge DC component, usually. And then you need really high dynamic range. And then you would need to do the Fourier transform afterwards. And you're just adding more numerical problems that could possibly happen. So you could, but it won't work as well. So why do it? What you can't do is one in the real space and one in the Fourier space. That's too far.
Next time, please, here again.